So trig identities, you actually know the whole left side. You know the basic trig identities already. We've been talking about these now for a few days. So you probably don't need to write those down because you should already have them down somewhere. But we know that secant of theta is the reciprocal of cosine, so it's 1 over cosine. You know that cosecant of theta is the reciprocal of sine, so it's 1 over sine. You know cotangent of theta is the reciprocal of tangent, so it's 1 over tangent. And then we also have already talked about that tangent of theta is sine over cosine, and cotangent is then cosine over sine. So those are all our basic trig functions that we've already talked about. We have some Pythagorean identities, and these actually come from our unit circle. So our unit circle, we had a radius of 1, right? So if here's a little diagram of our unit circle, our radius is 1, and we had all these different points along it. What did each point stand for? Yep, the cosine and the sine value. So each point stands for the cosine value and the sine value. Okay. So if we were to think of this, of each point as a right triangle with a hypotenuse of 1, your cosine value would be the length of one of the legs, and your sine value would be the length of the other leg. And then what would your Pythagorean theorem say there? Pythagorean theorem, a squared plus b squared is c squared, right? Yeah. So cosine squared plus sine squared should equal 1 squared, which is just 1. And that's where our first Pythagorean identity comes from. Sine squared of theta plus cosine of squared of theta equals 1. The order that you write sine squared and cosine squared, does that matter? No. So you could see cosine squared plus sine squared. It still is going to equal 1. Okay. And then there are two other Pythagorean identities that all stem from our original. I'm going to show you how they stem from it. The first one here is tangent squared of theta plus 1 is secant squared of theta. So all what we did to get this is we took our original Pythagorean identity, sine squared plus cosine squared equals 1, and we divided everything by cosine squared. So we thought sine squared of theta plus cosine squared of theta equals 1, and we divided everything by a cosine squared. That's a perfectly legal move. Okay, we can do that mathematically. We can divide everything by the same value. And then what does sine over cosine actually equal? Sine over cosine is tangent, so there we have tangent squared. Okay. Cosine squared over cosine squared, what would that simplify down to? Well, they're the exact same, so it would just simplify down to 1, so plus 1. Equals 1 over cosine squared. Well, which one's the reciprocal of cosine? Secant, so equals secant squared. So the second Pythagorean identity followed from our original just by dividing everything by cosine squared. And it's the same idea for our last Pythagorean identity, the cotangent squared one. What do you think we divided everything by this in this final case? Instead of dividing by cosine, we just divided by sine. So if we have sine squared of theta plus cosine squared of theta equals 1, if we divide everything by sine squared, well, sine squared over sine squared, what does that equal? 1. So here's our 1. Plus cosine squared over sine squared. Well, what does cosine over sine simplify down to? Cotangent. So there's our plus cotangent. And then 1 over sine squared. Sine is the reciprocal of cosecant, so equals cosecant squared. So these are our three Pythagorean identities. And we're going to use these to help us find missing information and also then to simplify things down. Okay? So you'll want to have these three written down. You can do everything with a sine squared plus cosine squared equals 1. Everything we do today, you can do it with just that single identity. But I like using all three because sometimes one of the other two will just lend itself to only be like one step instead of 4 or 5 steps. Okay? And you can easily see where they all came from based off that. All right. So we are going to find the cosine of theta if I tell you the sine of theta is negative 3/5, and we're in between 90 degrees and 180 degrees. And we're going to use our Pythagorean identities to do this. Okay. Now, we did problems like this where we had to write the other 5 trig ratios by making a right triangle. That's certainly one way how you can do this. Now we're going to see another way how we can do it. Okay. When it comes time for your test, unless it tells you specifically the way to do it, you can choose whichever way you want to. All right. So we want to find cosine of theta. We know sine. So is one of these Pythagorean identities just have sine and cosine in? The first one. So we're going to use the first formula. Sine squared of theta plus cosine squared of theta equals 1. We're going to plug in what we know and solve for the other. Okay? So what do we know? We know sine. Sine of theta is negative 3/5. So we are going to plug sine of theta in as negative 3/5. So negative 3/5, and it's sine squared. So squared plus cosine squared is equal to 1. Well, what's negative 3/5 squared? And we just have to square the top, square the bottom. Yep, 9/25 plus cosine squared of theta is equal to 1. How do you get cosine alone? Yep, subtract 9/25. Okay, so if we're subtracting 9/25 from 1, remember when you're dealing with fractions, you always want to think about common denominators. So if this is 1, you really want to think about it as 25 over 25. So we have the common denominator there. And what do we get? Cosine squared of theta should be equal to 16/25. And then how would we just get the cosine alone? Square root it. Sine cosine of theta should equal what? 16/25 would, square root of that would be what? 4/5. And then what do you think this in between 90 and 180 was talking about? No idea? In between 90 and 80 was talking about where this is on the unit circle, so that we know whether or not to make it a positive measurement or a negative measurement. And I just realized that there's a typo on this one. This one actually should say in between 180 and 270. Does anyone know why that was a typo? What are the sine values in the second, in between 90 and 180? 90 and 180 is right there. So your sine values up there are actually positive, and it was listed here as negative. So there is a typo. That's okay. So we're in between 180 and 270. So you want to think down here in the third quadrant, in between 180 and 270, what type of sines are our cosine values? They're negative, right? Cosine and sine are both negative here. So that means we want to make sure that we make the cosine a negative value.
So if it was negative, it could also be on the right? Like the fourth quadrant?
If the sine was negative?
Yeah.
Yeah, it could have also been in the fourth quadrant here, yeah. I made a typo when I created the problem.
Are we ever going to have to say which quadrant it is?
No, I would always give you the quadrant it's in, and then you would have to decide if it's positive or negative because of that. All right. Is that okay? Okay, so let's look at another one. This time we want to find cosecant of theta. If cotangent of theta is negative 1/4, and we are in between 270 and 360. So we want to find cosecant, and we know cotangent. So the first thing we want to do is look at our three identities and decide if there's one that has cosecant and cotangent together. The last one. Okay, so we will use our last identity. So cotangent squared of theta plus 1 is equal to cosecant squared of theta. We know cotangent is 1/4, so we'd say negative 1/4 squared for cotangent squared plus 1 should equal cosecant squared of theta. Well, what would be negative 1/4 squared? Yeah, so now we have 1/16 plus 1 is cosecant squared of theta. 1/16 plus 1 is 1 and 1/16. But we want to leave these as, we want to write these as improper, so we can easily take the square root of both sides. So what would be 1 and 1/16 as an improper fraction? Yep, 17/16. Is the cosecant squared of theta. And then how would we just get the cosecant? Square root it. So cosecant of theta would be what? Do we know the square root of 17? No. So square root of 17 over 4. And then once again, you want to think about your quadrants. This time we're in the fourth quadrant. What type of signs do we have in the fourth quadrant? Because we're in between 270 and 360. Here's 270, here's 360. So here your cosine values are positive and your sine values are negative. Which one's cosecant the reciprocal of? Sine. So we are going to follow the sine value, so we would make this negative. So you put a negative sign on it, and there's the cosecant. So if we wanted to use the first formula for this one, you'd have cotangent, so then you know tangent. And then from there, you know tangent is sine over cosine, so you would have to convert this formula right away to get tangent by dividing everything by the cosine. So it's possible to do it from the first one, but it involves the manipulation that we showed on that first slide. All right, let's do a couple more of these. We want to find tangent if we know secant of theta is negative 2, and we're in between 180 and 270. So we want to find tangent. We know secant. So the first thing, is there an identity that has tangent and secant in? The second one? Okay, so we're going to use the second one. So tangent squared of theta plus 1 is equal to secant squared of theta. We know secant is negative 2. So we have tangent squared of theta plus 1 is equal to negative 2 squared. So it's negative 2 squared? 4. So tangent squared of theta plus 1 is equal to 4. How do we get the tangent alone? Subtract 1. So tangent squared of theta is equal to 3. And then how do we get tangent? Square root. So tangent of theta is the square root of 3. And then we are in the 180 to 270, third quadrant. So what are our signs for cosine and sine in the third quadrant? Both negative. And how do we get a tangent from sine and cosine? So we divide them. So what happens when we divide two negative numbers? They cancel and becomes positive. So we would just say tangent of theta is our positive square root of 3. Is that okay? All right, we'll do one last one like this, and we'll get to simplifying them. We want to find sine of theta if we know secant of theta is negative 2. And we're in between 90 and 180. So the first thing we want to look for is, do we have something that has sine and secant together? No. So here's a case where we're going to have to try to manipulate some of these to our benefit. So then I want you to look for, if we have secant, what can we find? If we have secant, what could we find? If we have secant, we can find tangent. Does that help us get sine? I mean, tangent is sine over cosine, but then we would still need to know what cosine is, right? So that sounds like we're going to be at least 3 steps in, maybe 4. So let's look at it the other way. If we know secant, what other function do we know? What's the reciprocal of secant? Cosine. So we know secant, so that tells us we actually also know cosine. What would cosine be?
1/2.
Yep, negative 1/2. So now if we know cosine, can we find sine? Yeah, we can do that using the first one. Did that make sense, how we went through and decided which one would be the best to use? Okay, so once again, so we knew secant. We knew secant so we could find tangent, but that doesn't directly give us sine, so we won't use that one. Instead, we'll think since we have secant, we also know cosine because they're reciprocals. If we have cosine, we can find sine. So, sine squared of theta plus cosine squared of theta equals 1. And we know cosine squared. So sine squared of theta plus negative 1/2 squared is equal to 1. So how are we going to solve this? Okay, first we got to square the negative 1/2. So negative 1/2 squared is what? 1/4. Remember, whenever you're squaring those negative numbers, it's always going to be positive. How would we get our sine squared alone? Okay, subtract the 1/4. So what's 1 minus 1/4? 3/4. And then we have sine squared, so how would we get sine? Square root it. Yeah, so the sine of theta is the square root of 3 over 2. And we are in between 90 and 180. So second quadrant, so what type of signs do we have in the second quadrant? Negative cosine, positive sign, so this would stay positive. Now, does anyone see another way how we could have got this? Maybe a smidgen quicker. If you know cosine is negative 1/2, that is one of our special points on the unit circle. Every time either our cosine or sine is 1/2, what is the pairing with it? So for every point, if we had a half for one of the points, what was the other point? Square root of 3 over 2. One might have been positive, one might have been negative, but these two always go together. So if you ever see that either the cosine or the sine is a half, you should be able to automatically answer that the other one is square root of 3 over 2. Similarly, if you see a cosine is square root of 2 over 2, what does your sine have to be? Square root of 2 over 2. You just have to figure out if it's positive or negative then. Because those are always pairings that are along the unit circle. So it's perfectly fine if you use that logic as well. Does that make sense? Okay, let's try simplifying with these then. So simplify each expression. So essentially what we're doing here is we want to get this down as far as we can. So we just have one term left. Occasionally we'll have 2 terms. But for most of these we should be able to simplify it down to just one term. So here we have cosecant of theta times cosecant of theta. That's currently in 2 terms. Okay? So the way how we're going to simplify these down is we're going to want to change everything to sines and cosines and then see what other type of identities we have. So cosine of theta times cosecant of theta. Cosine is already a cosine. So cosecant, what's that the same as? The reciprocal of sine. So we can change this to say cosine of theta times 1 over sine of theta. Okay, so you just change it with what it's equal to for its identity. If we write this as one fraction now, what would we have as one fraction? Yep, we would have cosine over sine. What identity is cosine over sine? What function is that?
Tangent.
Not tangent, it's cotangent. So we can replace it with cotangent. So there we took cosine times cosecant. We manipulated and got it to just be cotangent. All right, let's try another one. Sine of theta times cosecant of theta minus sine of theta. Cosine over sine, or 1 over tangent. Cotangent is cosine over sine, or 1 over tangent. You can look at it in either way. So sine of theta, and then in parentheses, cosecant of theta minus the sine of theta. So first off, what is, we have a cosecant in there. So cosecant of theta, which one is that the reciprocal of? Sine. So what should we replace cosecant with? 1 over sine. So sine of theta, and then in parentheses, 1 over sine of theta, and then minus the sine of theta. What do you think you'd want to do with the sine of theta in front of the parentheses? Yeah, probably distribute it. So we distribute it, and then we would have sine of theta over sine of theta minus, what would be sine times sine? Yeah, sine squared of theta. Well, what would sine of theta over sine of theta simplify down to? Just 1. They're exactly the same. So we have 1 minus sine squared of theta. Whenever you get something that has a 1 and a sine squared, or a 1 and a cosine squared, you kind of want to think about this first identity up here. Does that first identity have 1 and a sine squared in? Let's try to rewrite that first identity so it looks like that. So right now, it says sine squared of theta plus cosine squared of theta equals 1. How could I rewrite this so that it says 1 minus sine squared of theta? Yep, subtract the sine squared of theta over. So cosine squared of theta equals 1 minus sine squared of theta. So what does 1 minus sine squared of theta equal? Cosine squared of theta. Okay, so we used our identity right here. We use that identity to replace it. So the identities, they work as they are, but they also work rearranged in different orders. Okay, so you can rearrange them to suit your needs. So there we want it rearranged so we could. Okay, how about 7? Secant of theta times cotangent of theta times cosine of theta. So what do you think we should do with the secant and the cotangent? Okay, so write them as sines and cosines. So secant we could write as what? Yep, 1 over cosine of theta. Cotangent, 1 over tangent, but that's still not in sines and cosines. So in sines and cosines, how could we write it?
Cosine over sine.
Cosine over sine. And then just times our cosine. Do we see anything that cancels?
The cosine.
Okay, so one of the cosines will cancel. It doesn't matter which one we cancel, so I'm going to cancel the first and the last. The ones would also cancel. Sure. So we're left with just cosine over sine, which is what? Cotangent. Is that okay?
So your answer doesn't have to be like a cosine or sine?
No, your answer doesn't have to be a cosine or sine. It just has to be down to like one term. Sometimes we'll have 2, but most of the time we'll just have 1. All right, we'll do 2 more of these together. Cosecant squared of theta minus cotangent squared of theta over cosine squared of theta. So now, especially when we see things that are all squared, that tells us we're using the Pythagorean identities somehow. So when everything is squared, we want to be thinking of the Pythagorean identities. So our numerator has cosecant of theta and cotangent of theta. Is there one of these identities that also have those two in it? This bottom one. So let's take this bottom one and see if we can somehow rewrite it as cosecant squared of theta minus cotangent squared of theta. So if we want cosecant squared minus cotangent squared, what would we have to do? Yep, just subtract the cotangent squared over. So we would have 1 equals cosecant squared. Oh, what happened there? 1 equals cosecant squared of theta minus cotangent squared of theta. Is that what our numerator currently says? So what can we replace this numerator with? Yeah, we can replace that with just 1 over cosine squared of theta. Okay, so we have a cosine squared of theta in the denominator right now. So since we have that in the denominator, what's cosine squared of theta a reciprocal of? Yeah, secant. So instead of writing 1 over cosine squared, what could this be?
Secant over 1.
Yep, see. So just secant squared. If the cosine is squared, the secant also has to be squared. Is that okay? All right, we'll do one last one. 1 plus tangent squared of theta over 1 plus cotangent squared of theta. So once again, we have values that are squared. So what we want to do is we want to see if we can replace them with any of our Pythagorean identities. So 1 plus tangent squared, what would that be the same as? Yeah, that's the same as secant squared. So we're going to replace that with secant squared of theta over 1 plus cotangent squared. What's that the same as? The last one. That's going to be the same as cosecant squared of theta. Okay. Now we have secants and cosecants. What do you think we should do with those? Switch them. They're reciprocals of either cosine or sine. So which one is secant the reciprocal of? Cosine, which means where would the cosine be? In the bottom. So we'd have a cosine squared of theta in the denominator because it's the reciprocal of secant. What is cosecant the reciprocal of? Sine. So cosecant is currently in the denominator. So that means sine would be where? In the numerator. And now we have sine over cosine. And that's tangent. So tangent squared. So there we simplified it down just to 1. Exactly. Yep, it's tangent squared because we have both the sine squared and the cosine squared. Those squared stay with it throughout.
So you just did like the secant really?
The secant is the reciprocal of cosine. So cosine went in the denominator because it's reciprocals. Cosecant is the reciprocal of sine. So the sine would end up in the numerator.
Okay.
Because reciprocals just means that they're flipped.